Force. We hear the usage of this term more often than not in our day-to-day life. We might not know that we are using it. Opening a door, riding a bicycle, lifting an object, all these require a force. What is force? Consider a ball lying on the ground at rest. You want to pass this ball to your teammate who is standing on the other side of the pitch. How will you do that? You need to make this ball move in the direction of your teammate. So you will kick the ball in the direction of your teammate. When you kick the ball, we say that you applied a force on the football. Here, the kick is nothing but the force you applied on the ball. Now consider another example. Suppose you have a desk at a point A. A person wants to move this desk from point A to point B. Again, how will he do that? Here, he will push the desk towards point B. In this case, we say that the person applied a force on the desk in order to shift it. The push here is nothing but the force that the person applied on the desk. Similarly, when you lift some object from the table, we say that you applied the force on that object. Here the force applied in the form of lifting. So forces are nothing but actions such as kicking, pushing, lifting, etc. performed on object. There are many such actions that we can perform. While riding a bicycle, we pedal it continuously to keep it in motion. Here, pedaling is the force that we apply on a bicycle. Hitting a hammer on a nail is also a force applied on a nail. Even stopping the ball means we are applying a force on it. We applied the same force to stop the ball. We applied some force to stop the ball. Opening a drawer, plucking a string of a guitar, moving a piece on a chessboard are some of the other actions performed on objects. So performing these actions on the objects is nothing but applying force on them. We can categorize all these actions into two basic ones, namely pushing and pulling. For example, we pull the knob of the drawer to open it. Similarly, when you are drawing or lifting a bucket of water from the well, we are pulling the bucket towards us. What are the actions that can be described under the pushing action? Passing the ball, hitting the hammer on the nail, etc. can be thought as pushing an object. Are there any actions that can be described under the both? Yes, there are. Suppose there is a book on a table, you can either pull it towards you or push it away. So moving an object can be described under both. Similarly, opening or shutting a door can be thought of as both. Similarly, opening or shutting a door can also be thought of as both. At this point, we can say that forces are nothing but push or pull applied on objects. Forces are due to interaction between the bodies and objects. For example, in order to move the desk from point A to point B, he must interact with the desk. Therefore, force is nothing but push or pull of an object resulting by interaction between two objects. Take a stationary object for an instance. There is a 10 newtons of force acting on it in the upward direction and a 10 newtons force acting on it in downward direction. Is the object moving? If yes, then in which direction is it moving? The answer is it's going nowhere. We see that there is more than one force acting on the object. The two forces are acting on the object are equal in magnitude. What about the directions? One force is acting on downward direction and the other is acting on the upward direction. So both the forces are opposite to each other. So we can see that the object is under the influence of equal and opposite forces. The object is not moving because these equal and opposite forces cancel each other out. As the forces cancel each other out, we say that forces are balanced and net force on the object is 0. Now look at the second object. There is a 15 Newton force acting on it in the upward direction and a 20 Newton force acting on it in the downward direction. Are the forces balanced here? No, They are unbalanced because they don't cancel each other out. What will be the net force here? It will be 5 newtons downwards. 20 minus 15 is 5. As the downward force is more in magnitude, the net force will be 5 newton downwards. This tells us that if two forces act in opposite directions on an object, the net force acting on it will be the difference between two forces. Suppose that you want to move a pretty heavy load and you are alone. What would you do? You asked for help, right? So you and your friends together move the load easily. What is the reason for this here? There are two forces acting on the desk, yours and your friends. Both the forces are acting on the same direction. Both the forces combined together produce a greater net force. Remember, if the two forces are acting on the same object in opposite direction, then the net force on the object will be the difference between the two forces. And if the two forces are acting on the object in the same direction, then the net force of the object will be the sum of the two forces. It is at rest and not moving in any direction. In order to move this ball forward, you have to apply a force. So you apply a force by pushing the ball in this direction. What happens after you apply the force? The ball starts moving in the forward direction. Initially, the ball was at rest, but now it has started moving. What can you conclude from this? We can say that force can make object move from rest. In other words, force can set objects into motion. It was the force that you applied on the ball it made to move from its stationary position. Suppose we apply the force on this moving ball and the applied force is in the same direction of the motion of the ball. Will the speed of the ball increase or decrease? The ball starts moving with a greater speed. What can you conclude with this observation? We can say that force may increase the speed of an object. The force was applied in the same direction and hence the speed of the object increased. But can force decrease the speed of object? Of course, if you put your hand here now and obstruct the motion of the ball, what do you see? The ball reverses its direction and moved a little before stopping. What you can conclude from this? If the direction of the force applied on an object is in the opposite direction of the movement of the object, then the velocity of the object will reduce. In this case, the direction of the force is opposite to the motion of the ball. So the force changed the direction of the motion of the ball. The force not only changed the direction of motion but also reduced the speed of the ball. You see that the ball stops moments after the colliding with your hand. We can conclude two things from this. First is that force may decrease the speed of an object, and second, force may also change the direction of motion of the object. In fact, it not only decreased its speed but also changed direction. Here are the things that can happen when we apply force on objects. Force may move object from its rest position. Force may change the direction of an object. Force may increase or decrease of the speed of an object. And force may cause more than one of these. Here we have a sponge ball, which is almost a perfect sphere. Now hold it in your hand and press it. Is it a sphere now? Not really. We see that it has lost its spherical shape and now has this odd looking shape. When you release the ball, it returns back to its original shape due to its elastic properties. So when you press this ball, you applied a force on it, and the force called a temporary change in the shape of the ball. Now instead of a sponge ball, let's take a piece of dough and perform the same experiment. Hold it in your hand and try to press it. The piece of dough obtains a new shape. However, in this case, when you release the dough, it does not retain its original shape. It remains deformed even after you have released it. So, here we can say that force causes a permanent damage to the shape of the dough. In order to overcome this change, that is, to restore the dough to its original shape, we need to apply an external force on it. From these two experiments, we learned that force can cause temporary or permanent change in the shape of an object. In fact, if an object undergoes any change in its shape, then it means that some force is acting on it. An object cannot change its shape by itself. Force is required to do that. When we sit in a bean bag, it changes its shape. We change the shape of the tube of the toothpaste when you press it in order to get the paste out. These objects, which regains their original shape when the force is removed, are called as elastic materials. Here wants to pass this football towards his teammate who is standing on the other side of the pitch. The player will apply force on the ball by kicking it. When the player applies the force, his foot is in contact with the football. So this is a contact force. Other examples of contact forces can be pushing or pulling the desk from one point to another point. Our hands are in contact with the desk. Similarly, pressing the keys in the keyboard, moving a piece on a chessboard are some of the other examples in which part of the body are in contact with the objects. In all the examples we have seen till now, it is a part of the human body that is in contact with the objects, and the force is generated by your body. These kind of forces are called as muscular forces. The muscles in our body expand and contract when we apply these forces. Muscular force to carry out physical activities. A bullock cart is used to carry load from one point to another. Bullocks are tied with the cart on. The load is then added to cart. The bullock then applies muscular force on cart and moves it forward. Another contact force that we can talk of is the force of friction. What is force of friction? Try rolling the ball on a horizontal glass surface. What do you notice? You notice that ball gradually slows down after some time and eventually comes to a halt. Why does this happen? Why doesn't the ball continue to move in the same direction forever? The reason for its slowing down and ultimately stopping is the force that this surface supplies on the ball when it is moving. Yes, the surface supplies the force on the ball and the direction of this force is opposite to that of the motion. So, when the ball is traveling toward the right, the surface is applying a force towards the left. The force applied on the ball, it is called as the force of friction or simply friction. So muscular force and friction are examples of contact forces. Take a bar magnet and place it on the table. Place an iron nail on the same table at some distance away from the bar magnet. Now move this bar magnet towards the nail like this. Keep moving the magnet slowly and closer to the nail, but make sure not to touch the nail. What do you notice? When the bar magnet was sufficiently close to the nail takes a leap towards the magnet and sticks to it. What does this tell us? This shows that magnet attracts the nail and the contact is not necessary for this attraction. The magnet pulled the nail towards it even though it was not in contact with the nail. The force that this magnet exerts on the nail is called the magnetic force. So contact is not required for the magnetic force. We take another example. When you release an object, say a plastic ball, from some height above the ground, it just falls on the ground. Why does it fall on the ground? This is because the force that Earth exerts on it in the downward direction. The Earth always pulls the objects towards it. This force that the Earth exerts on an object is called the gravitational force. This force is attractive in nature. That is, it attracts two objects towards each other. When you open a tap, water begins to flow downwards. This is because the gravitational pull of the Earth on water. Now I want you to tell me, is gravitational force a non-contact force? Yes, it is. We can clearly see it from our examples. Contact is not required between the Earth and the other object to attract each other. Therefore, gravitational force is a non-contact force. Take two balloons and suspend one of them in the air by means of a thread. Now hold the other balloon by thread tied to its one end and bring it near the other balloon. What do you notice? Do you see any force between them? Nothing in particular. Now rub the free balloon which is in your hand with a woolen cloth for some time. After that, bring it near the suspended balloon. Do you see anything strange now? Yes, both the balloons are attracting each other. Something must have happened to this balloon after we wrapped it with the woolen cloth. We can say that this balloon acquired something from the cloth after rubbing, and that something is what we call as electrostatic charge. So this balloon is charged now, and this charge is responsible for the force of attraction between the two balloons. What about the suspended balloon? We call it the uncharged balloon. It doesn't have any charge as we haven't rubbed it with anything. Now wrap the suspended balloon also with an woolen cloth. It will also be charged. So we have two charged balloons now. Bring them together. What did you see? Now both the balloons are moving away from each other. They are repelling each other because of the force that is acting between them. What can we conclude from these two experiments? In the first place, there was a force of attraction between charged and the uncharged body. In the second case, there was a force of repulsion between both the charged bodies. In fact, whenever we rub two bodies together, both of them acquire charge. Then this charge attracts or repels other charged or uncharged bodies when brought near them. This force exerted by a charged body on another uncharged body is known as electrostatic force. The electrostatic force can either be attractive or repulsive in nature. Is electrostatic force a non-contact force? Yes, it is also a non-contact force. When you hammer an iron nail, you apply the force on the flat side of the nail. The pointed side of the nail, which is in contact with the wall, then applies the force on the wall and tries to pierce it. What will happen if you hammer the pointed side of the nail and try to pierce the flat side of the nail? You will find it is difficult to push the flat surface of the nail through the wall. Even if you apply more force than you did in the first case, you might not be able to pierce it through the wall. What is the reason for this? The reason is that the pressure applied by the tip of the nail on the wall is more than the pressure applied by the nail's flat surface. But why is this? First, notice the area of the tip of the nail is very less as compared to the area of the flat surface. This tells us that the area of the surface on which the force is applied matters. Now let us define pressure. We define pressure as the perpendicular force acting on the surface of the object per unit area on which it is acting. It is a force acting per unit area. We already know SI unit of force is Newton, denoted by N, and the area is meter square. So unit of pressure is Newton per meter square. It is also called as Pascal, which is denoted by PA. Why is it called Pascal? It has given this name to honor the achievements of a French scientist named Blaise Pascal for his contribution in the state of hydrostatics and hydrodynamics. Say there is a water kept in a plastic container. Let us divide the fluid into 5 equal parts. Make a hole in each layer. What do we notice? The water is leaking out of the 5 holes, which must be pretty obvious to everyone. But the reason for this leakage is the pressure that the water is exerting on the walls of the bottle. So the liquid exerts pressure not only in the downward direction but sideways too. Moreover, notice the distance covered by the water flowing out from each hole. The water coming from the bottom hole covers the maximum distance, while the distance decreases as we go towards the top. What does this tell about the pressure? This tells us pressure is higher at this point compared to other points. The pressure increases as we go downwards. So what did we learn from this video? We learned that liquids apply pressure and they exert pressure in all directions. We are surrounded by air from all directions. This envelope of air around us is what we call as atmosphere. Does air also exert the pressure on objects on the earth? In our previous video, we have studied that liquids exert pressure in all directions. Just like water, air is also being pulled on by the Earth's gravitational force. This force applies pressure on the air in the downward direction. the pressure is exerted by air is called as air pressure or atmospheric pressure. Did you know that the atmosphere is divided into different layers? The atmosphere is divided into 5 layers, namely troposphere, stratosphere, mesosphere, thermosphere and exosphere. The pressure in the troposphere, which is the bottommost layer, is higher than the pressure in the layers above it. And I am sure you can guess the reason why. This is because the weight of the air above the troposphere is greater than the weight of the air above, say, stratosphere. The air pressure also acts in every direction and not only in downward direction. And finally, just like the pressure in liquids, the air pressure at particular height above the Earth's surface is same in all directions. That is, if I take these 2 points at the same distance above the Earth's surface, then the air at this point will exert equal pressure in all directions, just like the air at this point. Let's look at an interesting graph now. A graph which represents pressure at a particular altitude. The troposphere is the closest surface on the Earth, and the pressure in this layer goes up to 1 lakh Pascal, where Pascal is represented by PA is the SI unit of pressure. This is massive pressure. This pressure pushes and pulls the objects on the surface of the Earth. For example, if I take a table with the upper surface of 1 by 1 meter, the pressure exerted by the air on the table in downward direction is greater than 1 lakh pascals. This is equal to 10 cars being put on the table. I know what you must be thinking. Why doesn't the surface collapse under this huge pressure? How does it handle such massive pressure acting down on it? A little while ago, we said that the pressure is exerted above a point on the Earth's surface is equal in all directions. So the pressure at every point on the table is same in the all direction. That is, the downward pressure is pushing the table with a greater force, then the upward pressure is also pushing it in the upward direction with the same force. Both these forces are balanced and table does not collapse. As I said, pressure is not only acting in these 2 directions. It's acting on the surface in all directions. Pressure is acting in the opposite direction, cancel each other out. Here is a cool experiment that you can perform at home. Take a plastic bottle filled with water. Take a cardboard paper and place it in the open end of the bottle, just like this. Hold this paper with your hand so that it does not move from its position and invert the bottle. Now let go of the paper. What do you see? The cardboard sticks to the surface. Why is it held to the surface? It is held to the surface because of the air pressure that is pushing the paper in upward direction. The upward air pressure is sufficient to counter the downward push exerted by the water. Now make a few holes in the bottle. What happens now? Why did the paper fall off? Did the pressure on it stop acting? Or did it reduce in value? No, it didn't. The upward pressure on it by the air remains the same, but the downward pressure increased it in its value. When we made holes in the bottle, we allowed the air to flow inside from the top. The air from the top started exerting pressure on the water. The combined pressure of the water and the air from the top could easily overcome the pressure exerted by air in the bottom. Hence, there is a net force acting on the paper in downward direction. That is, there is more pressure in downward direction, and that's why paper gets detached from the surface.